already said, I'm going to talk today about multilevel stochastic gradient descent, partially for risk-averse, but in general for PDE constraint optimization problems. And also I want to mention that this talk is the result of joint work together with Niklas Baumgarten, and in the second part with Niklas, Philip and Tommaso. And yeah, let's begin. Since maybe some of you don't actually have something to do with PDE constraint optimization, I want to give a quick motivation about why we want to do this or what's behind all of this. And first of all, in this process of the optimization, we consider some inputs omega and c, where omega is here given by some Gaussian random fields. And we put this into a system of a PDE that gives us some state u that is depending on the control c that we got here. The c for the moment is free to choose, but the question is, what is the goal to reach? And the goal is that, for example, we have some target state that we want to reach in any circumstances, or that we want to get as close as possible for every case of omega, for every case of our omega for the forward problem as possible. And this talk will be about how to solve this mostly effective with a multi-level estimator for stochastic gradient descent, and let's begin with this. First of all, the mathematical setting. We consider, of course, PDE settings with a domain, some probability space, Hilbert spaces V and W, and our target state D in the larger Hilbert space. And mathematically speaking, the optimization problem we are considering is that we have some risk measure R, that is over here, of the sample-wise distance between our state and our target state, where the state is the solution of some linear uncertain PDE system, together with some cost functional that is likewise can also have been seen as some regularization term. Now, for the first part, we will talk only about the risk-neutral measurement with just the expectation. But of course, you could be also interested in having the opportunity to optimize for a more risk-averse case, where you don't want to, where you want the worst case to be don't as far off from the actual target state as in the risk-neutral case. Also, throughout this talk, we will consider an example for G with the elliptic equation with log normal coefficients y. Where the log normal or the Gaussian random fields for the log normal coefficients will be sampled with an SPDE sampling on a unit square with these Hilbert spaces. Already, as seen, the target state is given by this function d with a combination of sinus functions in the components. And down here we can see again two samples of the Gaussian random fields as well as an approximation for the optimal control that we computed in the end. Now, how do we actually solve this? And of course, many know how to solve an optimization problem, because if we know that R is in some form convex, that we get mostly for the expectation, or that we get for the expectation, we have the optimality condition that if the gradient of our target functional large J is equal to 0, we have found the optimal control. And the gradient in this case is calculated by our derivative of the cost functional minus the expectation of the adjoint state. Now the question is, what is the adjoint state? The adjoint state is the solution of the adjoint system with the right-hand side d minus u. This can be calculated if you take the Lagrangian functional and take the adjoint equation and the Lagrangian functional for large J and take the adjoint system into perspective, you come to this equation. Now, Of course, at this point, it's really hard to actually calculate the gradient because we want to do it numerically, and right now we can't do it. So what we have to do in this process is we want to find a solution by an efficient discretization of the system, afterwards optimization, and then estimation. The discretization is done with finite element methods, in particular linear Lagrangian elements, using the finite element library M++. Second of all, to the optimization process. For the optimization, we are using a gradient-based optimization algorithm, in particular what we call a stochastic gradient descent. This is widely discussed what actually counts as stochastic gradient descent, but throughout this we will talk about it as some form of the actual gradient where we exchange the expectation back here for some estimator, because right now also we cannot just take the expectation we've got there. And to actually estimate this, we considered 3 different approaches. The first approach, which is in most literature known as stochastic gradient descent, is the approach of Robbins-Monroe for PDE problems already done in the work, only for example from Caroline Geiersbach and Winnie Fried-Wollner. It's a simple approach that is converging pretty fast, but has also a very high variance and brings absolutely no uncertainty quantification in the process. The second approach of a batch stochastic gradient descent, also discussed in the book of Bourdieu, is what we will be using as a baseline algorithm to see what can be done with this and to see what results we will get with this. And of course, the third approach that we will be mainly taking a look at is the multilevel stochastic gradient descent, where we use a multi-level estimator to estimate the expectation in the process of gradient determination. This work has already been done in the work of Van Barel, but we will take a further look on that later. Or we will take a further look into that topic later. So, first of all, for the batch gradient descent, or for the baseline algorithm, like I already said, we just take a Monte Carlo estimator in the process of the gradient estimation, where I quickly want to discuss that in the actual process, in the algorithm, we have to do a sample-wise computation of, first of all, of course, the sampling method, since we want to have some Gaussian random fields that we can put in. Afterwards, we have to solve the forward operator to get the actual state for the sample, and then we have to compute the adjoint state that we can use for the gradient. So in each of these, we have to solve at least 2 PDEs and have to do this for each sample. In return, we will get a Monte Carlo estimator of the adjoint state for the gradient, but as well as a Monte Carlo estimator of the target functional, since we can compute the target functional in the process of computing the forward operator. This approach, of course, is widely used and of course brings also some scalability with it. We can see here some experiments with different batch sizes for the Monte Carlo estimator, where we compare the estimation of the target functional on the left side and the estimation of the gradient norm on the right side, where we can see we've run the algorithms for 100 steps and have a log-log plot with the total computing time on the right-hand side. And we can see that, of course, like we would expect, if you take more samples in this, we can reduce the variance in the estimation. For the gradient, we get better results, and even the gradient estimation that can be seen as some form of an error estimate, since we want to reach the gradient as equal to 0, will even get smaller if we take larger batch sizes. But, of course, on the downside of increasing computation times, or increasing computing times. And now, as I think most people already have discussed earlier this week and also already know, we can exchange this Monte Carlo estimator for a multi-level Monte Carlo or multi-level Monte Carlo estimator, and therefore want to reduce the computational costs, but still reaching the same variance in the process of the gradient descent. And just a real quick a recap on what or how we define the multi-level Monte Carlo estimation for the adjoint state. Basically, the telescoping sum, like Sebastian told earlier, or what we understand with multi-level here is the level of discretization for the PDE system that we can see over here with corresponding mesh size that is getting smaller for a larger level. And now we can take the expectation on a level L and take the telescoping sum to split this up into different sums, but of course, since we're working on the actual state and not only for quantities, we have to use some projections here. Now, by using Monte Carlo estimation, in the process of that, we get the multi-level estimator for the adjoint state, and under similar assumptions that the discretization error, the sampling error, and the cost is bounded by the mesh size with some exponents. So it scales with the mesh size. We get, of course, the usual epsilon cost theorem that the mean squared error is bound by epsilon, or that we find epsilon squared. For every epsilon squared, we find the multi-level batch. So the mean squared error is the mean squared error is bound by epsilon squared at the cost of epsilon to the power of -2 in the best case. Of course, here normally should be the case of beta equal to gamma 2, but Now this work has already, or is of course known work, and now we want to discuss how this affects our estimator, or how we can leverage this to make a better estimator in the process. And there we come to the multi-level algorithm we did, where we exchange the real estimate, or the real expectation of the adjoint state by the multi-level estimation. And in the process of that, we have a similar algorithm than for the batched gradient descent, where we, but on behalf of that we have to use, we have to compute for each sample the solution on a level L and the level L-1 to actually get the difference for a telescoping sum. As a result, of course, if we return these Monte Carlo estimations into the multi-level estimator, we will get the multi-level estimation that we have here on the left-hand side. Now, to compare this to the computations we did earlier, we see on the left-hand side a computation or the comparison to the normal Monte Carlo method with 256 samples. That was the highest samples we did on earlier. And we can see for both the target functional as well as the norm of the gradient, at least the estimations, that for a similar variance in the process of that and a similar accuracy, we only need 10 to 20% of the computation time that we needed for the Monte Carlo estimation. So we can reduce the computation time in the process of getting similar results extremely. So that's one thing that we can get from that. But on the other hand, we can also see that we still have a scalability, since we have the plot here on the right side where we see if we quadruple the sample sizes on each level and append a level for the next batch or for the larger batch as well, we can likewise, for the Monte Carlo estimator, we can see that the variance reduces even more with larger batches, and even more the gradient estimation gets smaller. So therefore we can also get an error estimation that is smaller. So the results are getting better and better. For numerically speaking, we take a pause at this point because we now want to take a look at what is actually theoretically speaking possible for this. And theoretically speaking, we know from different works earlier, that in the best case with normal stochastic gradient descent, we can reach an error estimate with the order of 1 over k, where k is the iteration step. And in the best case, we can reach actually the linear convergence from deterministic optimization from the gradient descent, but this can only be reached with, or achieved with, sample average approximation, or one could also call it full gradient estimation, where you have to take a huge load of samples for the gradient estimation in the Monte Carlo process, so at an extremely high cost. So now, for us, we want to achieve this linear convergence, but by reducing the costs. And this can be done if we quickly introduce some notation that we will need later. We now want to, or we construct an increasing sequence of sub-sigma algebras of the filtration F in such a manner that our control in the cave step, either the actual control as well as the discretized control, are Fk measurable. This just means that we go, or in the process of the proof, we say we know the actual state of the control, so we know how we came to this point. And also we quickly take a new notation where we do the Bochner norm with a conditional of Fk. So now, by the usual assumptions that the small j from earlier is strictly mu convex, which is given if lambda is larger than 0, as almost sure for every sample, that is L2 Fréchet differentiable, and the gradient is Lipschitz continuous. Those are mainly the usual assumptions, as well as an assumption on the control, that we can actually assume that the control in the cave step is, in the discretized version, has a distance to the control in the cave step that is somehow bound by the adjoint state in the cave, or the distance from the discretized adjoint state to the discretized adjoint, to the non-discretized adjoint. This is the first assumption, and the second assumption is that in every step k, we have the multi-level Monte Carlo assumptions for the adjoint state. Basically, together with these two assumptions, we can show that we get, or that there exists, of course, a level L, the multi-level batch up to that level L, a step size Tk, such that we get the linear convergence for the discretized control in the cave step to the actual optimal control at a cost that is mainly determined by the cost of the last multi-level batch we took in the cave step. So basically, it's not even that hard, or it's, of course, we have some constants here that we would need to take a further look on that, but mainly the cost scales up only with the last batch, or mainly with the last batch. Now, since we have a lot of time today, or at least for myself, I got a lot of time today, I want to quickly go over the proof of that. And for that, we take a further look at the notation again, but for the first part, we just take a look at the scalar product split of our k+1 iterative of the error we got. Since we can split this with the scalar product of the conditional Bochner norm, we can split this into these parts. And now we want to get the multi-level estimator into some form where we can do where we can use the assumptions. So somehow we want to get this into the assumptions we did earlier, and therefore we can rewrite this as the multi-level estimator minus the true gradient in the cave step plus of course, the true gradient minus the gradient in the optimal control. And the gradient in the optimal control, as we know from earlier, is equal to 0, so that's why we can write this there. So now what we have written here is A being some form of the optimization error, since we use the gradient minus, in the case step, minus the optimal control gradient. And we can also rewrite the first part into our mean squared error, or into some form of the mean squared error of the adjoint state, as well as the discretization error of our cave control. So these three parts we can now use and use the MLMC assumptions from earlier as well as the other assumptions. So for B, I think it is pretty clear that we can just use multilevel Monte Carlo, the multilevel Monte Carlo assumptions to say there exists an epsilon k squared such that we can actually bound this by this. The second thing is that we can use the first assumption over here to bound the second part here, and then use the multilevel Monte Carlo assumption to get the same bound with some constant. The third part here, the optimization error, can be bound with the Lipschitz continuity of the gradient, and then again can bound similar to C and B into the MLMC assumptions. And now, using this together with the mu strongly convexity of, or the strongly mu convexity of the problem, we can estimate the whole gradient or the whole error of in the k+1 step by the error of the cave step, multiplied with some constant depending on tke, eta, mu, and tk. How did we do that? We actually, since we have not yet set the epsilon k, we can use this as the error in the cave step together with some eta that we just put up front. Now we can see that for this term we can choose the eta in any manner that we want to choose it. So we can choose this small enough so that for this row k we define here, we can find a tk that is positive, so a step size that is still positive, but the row k will get smaller than 1. So for eta sufficiently small, tk larger than 0, we get row k smaller than 1. And now if we choose row k, or the row, to be the supremum over all k's, and using Tower rule, we get the linear convergence we talked about earlier. So for this point, the convergence rate is proven. And now we want to talk about the cost. The cost can be written down as the sum of the cost over all steps. Now we know that the sum of the costs in each step can be bound by the epsilon cost theorem by the epsilon k to the power of -2. Since we have already chosen something for the epsilon k in each step, we can now rewrite this as the ek, which is proven to the first part, similar or in the order of rho to the power of k. So now we can exchange this for rho to the power of k, and by doing approximations with integrals, we can see that we have rho to the power of -2k -2, where we can just leave out the -2 in the end by saying it as some constant, where we come to the conclusion that in the best case, the cost for the multi-level estimation or from the multi-level stochastic gradient descent scales with the arrow in the last step to the power of -2 in the best case. Concluding this proof in the end. Now, this proof brings us 2 questions. First, or maybe one question in the end at all. We have chosen in each step multi-level, or we have proven that you can increase the multi-level batch in each step to get the actual error estimate we want in the end. And you don't have to choose the multi-level batch you want to have in the end from the beginning on. And this is something we can also see when we take a look again at the scaling experiment from earlier, that if we have the multi-level batch on the lowest multi-level batch with the lowest level, in the beginning the convergence of the gradient is pretty much as good as for the larger batches. So we don't need to use the complete computational power that we have for the largest gradient batch, and can start with smaller batches. This brings, of course, the idea of an adaptive scheme. But not only an adaptive scheme, since, I mean, if we take a look at this computations, those computations have all been done on a cluster with a large amount of nodes, or with a small amount of nodes in this case, but with a large amount of processors. And clusters bring us the problem that we have limited time and limited memory. The limited time, of course, because we can't block a cluster for several days and say everyone else has to do their work somewhere else. The limited memory is some problem you get from every working machine also at your home. And this brings us to the idea that we not only want to do an adaptive scheme for this, but also a budgeted scheme. So we say now we have a new problem, a so-called knapsack problem, where we say we want to find where CLK is the solution or the kth iterative of the multi-level scheme. We want to find a step size and a sequence of multi-level batches over the steps in such a manner that the error in the kth step will get minimized under the constraints that we have some limit for the computational time and the memory. Okay, how do we solve this, you might ask? By this clunk. Of course, in the first moment it looks a bit rough, or it's a bit rough to look at this, but let me quickly go through this. In the beginning, you just check if the computational time is already used up. And then, of course, we need some estimations for the numerical error and the sampling error, that we can get from the multi-level estimation. And we can check if the numerical error from the previous rounds of our iteration scheme is getting too large, we can append a level. If that's not the case, we can use the old level set, and we want to compute the optimal sample amount in the next step. This is done by an approximation from the old, or by the values we get from the old estimation round, from the previous step, and then basically by minimizing the cost estimation with the constraints that we still want to reach a certain error level that we get in the beginning with epsilon k. Now, if we get this optimal batch, we have, of course, to check if our constraints are still met. So we have to check, is our optimal batch with the estimation of the cost of the next batch, is it still feasible? Or do we go over our time budget? And also, of course, is the memory budget still feasible, or is the batch too large with the new level? So therefore, if all of this is met, we can do multi-level Monte Carlo estimation like we did earlier, together with some adaptive step size that is discussed in the work of Frederik Köhne and some other people. And can calculate the new error, and in the end we take our estimation of the gradient in the norm as our new epsilon k, so we can actually check that the error will also, that the sampling error will also scale down with the gradient norm and will also decrease with that. So with this algorithm we get these results. And these results compare the batch stochastic gradient descent with a constant batch size here, of course, in comparison to our budgeted algorithm. And the budgeted algorithm does brings us an enormous speed up and also an enormous increase in accuracy, since we can see that for our budgeted algorithm, of course, we take way less steps, but comparison in the total computing time, we see that we have a speed up of 18 times compared to the batch gradient descent, and in the end we get an accuracy that is 5 times higher than for the batch gradient descent. So compared to our baseline algorithm, we see already an increase in performance. Now, furthermore, we can also get some theoretical results for that, because we can actually bound the solution of this problem to the, we get a lower and an upper bound. The lower bound, of course, is set by the memory we've got on the machine, since if the memory is not enough to compute a new level, we cannot get any closer to the optimal control, since the discretization error cannot get any smaller. Now, on the upper hand, we have, or the upper bound is determined by the computational time, but also by the number of processors we are using, since we are running all of this parallel, and is also determined by the fraction of how much of our code is actually parallelizable. So, of course, if all of the code is not parallelizable, the number of processors don't bring any thing for all of it. Now, furthermore, the exponent here is given by the minimum of 1/2, or on the other hand, alpha over 2 alpha plus gamma minus beta, where we see if the exponent for the cost is getting larger than beta, then we will also have, similar to the multi-level estimator, decrease in convergence speed here. And this is now probably the most interesting for most people here, because we now have actually a plot where we see all our exponents in one iteration step. We see our alphas for the different for the adjoint state and the state over, so the numerical error decay for one iteration step. We see this the same for the sampling error, and we also see how our algorithm behaves with the samples, or with the total samples that it uses over one iteration step. Now, in comparison, what we see here is how the algorithm behaves if we use more and more processors. So, is it actually more scalable? What is the downside? Or do we get some downside if we use more processors? Or does it work perfectly fine? And what we see here over is compared, or is something we have seen earlier, is the estimation of our gradient in the norm, where we see that if we use more processors, the delta is actually getting worse, which is pretty much easy to explain, since we have more communication between the processors, and therefore we have to take more time into this context. But we still, of course, get a decrease in the gradient norm, so the algorithm performs better, but this will only go up to some certain point, since we also see the comparison from 64 to 256 processors has a large margin between it than the comparison of 4 times 256, so 1K processors. So at some point we will reach the limit of this algorithm and parallelize since we don't have the option to parallelize even more, since we are only running 2D elliptic problems. Okay, this concludes basically the first part, and now I want to talk a bit about the second part for how we want to use, or how we are using this for risk-averse problems. And just a quick recap, what we used earlier was here that we said R of j is equal to the exponential function of j, and just already stating here that we will use a KL expansion KL expansion in the next numerical results. But the question is, can we somehow get, or how can we motivate a risk-averse case? For example, if we say that we are not interested in that the expectation meets, the expectation of our state meets somehow, or the expectation of the distance will somehow get minimized, but we are interested in a worst case solution, so that we say for the samples that have a larger margin, we want this larger margin to be smaller, and therefore throw away some samples that maybe would be even pretty close to D. And this can be reached by taking some exponential, taking an exponential function and some parameter theta of j together with j, where theta is here giving us the, let's say, amount of risk aversion we've got. So the larger theta is, the more risk averse we are actually. And furthermore, if we convert this into the entropic risk measure, we have to use theta to the power of -1 together with the logarithmic function, due to the reason that for this risk measure we actually have the property that for theta to 0 we will still get the exponential function, and for theta to infinity we will get the essential supremum, which is basically the worst case solution we might be interested in. Now this, of course, like I already said, for this we will be using another generator for the sampling method, some form of truncated KL expansion, so we can show that this also not only works with SPDE sampling, and these the other values we will take as the same, so still unit square with the same target functional target state. And here we see that the samples for the truncated generator are a bit smoother than earlier, but we also see, for example, that the control is getting smaller and tends to lean more into 0 for a high theta. And of course, with a new target functional, we also have to calculate a new gradient. For this entropic risk measure, this looks like this, where we can use just a chain rule to compute this, and in the end we have the exponential of theta j times the adjoint state, where the adjoint state is computed as before. Now to the point. When we use directly the multi-level estimator on this, we of course have to use the multi-level estimator in the numerator as well as the denominator. And we will introduce some problems with that. If we will take a look, we will introduce some problems in a moment. For now, just we want to take a real quick look on the scaling experiment that we have seen earlier for this batch size, for the batch sizes, where we can see that the scaling experiment works. We will get, we will achieve an increase in the accuracy, but we will also see for a theta equal to 10 here that the theta also increases the variance of the estimator somehow. So we have to be a bit cautious, we have to be a bit careful with that. Also, where we have to be careful is in the proof of, or in the concept of the proof, since we have shown that for the risk neutral version we get linear convergence, but we cannot choose, or we cannot take this proof one-to-one on the estimator we have seen here. Due to the reason, if we take the same passage of the proof, we now have the comparison of the numerator and denominator with the expectation in both numerator and denominator, and of course cannot just bound this by the multi-level scheme. So we have dependencies in numerator and denominator, which brings us to a problem. Furthermore, this brings us to the problem of how do we now estimate the sampling error. So this will get us into a problem in the algorithm, and therefore will also give us the problem of how do we choose the optimal batch size, which is for now unclear. And unfortunately, or ideally, I would now talk about how we actually do this and how we have done this, but unfortunately, this is actual work in progress and not finished yet. And therefore, I have to leave these problems open for now. But what can I actually show you? Of course, this talk is not done yet. What can I actually show you is that if we take a kind of naive approach, where we ignore the fact that the multi-level estimator is also in the denominator and not only in the numerator, we can do a trick similar to the proof of the risk-neutral case, where we choose similar arguments with the adjoint state or an approximate adjoint state being defined by this, and then using similar multi-level Monte Carlo assumptions, we can actually get an error estimation for the sampling error and therefore can compute some optimal batch sizes for our multi-level Monte Carlo scheme for the budgeted algorithm. Now, the experiments for that are promising, but I say promising in this case because right now, of course, this uses the wrong sampling error, this uses the wrong estimation, and therefore is a bit problematic. But what we still can see that is that if we compare just different risk aversion parameters here, we can still see that the budgeted algorithm works even with the false sampling error estimation or with an incorrect sampling error estimation. And on the downside of the delta getting smaller and smaller for the risk aversion parameter getting larger and larger. But in the end, this is, in our view, this is promising. This is a good point to start at, to take a further look at. And so I can conclude this talk with these results and the outlook that we, of course, want to finish what we have got so far and do the linear proof, or the proof on the linear convergence in our in the iteration scheme. And also we want to do large-scale experiments where we can take even larger number of processors due to the reason that we have more scalable, parallelizable code. That's it for me. Thank you for your attention.